we're going to be on the DVD, we're showing some absolutely outstanding stuff when it comes to hydrogen and natural gas fueling and all fueling of internal combustion engines. But before we start, the people watching this, they gotta know internal combustion engine fundamentals.
Well, these fundamentals are age-old. They're what brings us around the world in matters of commerce and farming and in all other ways of basic transportation. We depend upon internal combustion engines. And what you can be sure of in this regard is that this internal combustion engine process is by now rather well understood but not comprehensively utilized in its best aspects for what we want to be doing.
Well, one thing we should talk about is really the miracle of the internal combustion engine that has been horribly demonized. Would you say we're about in our 5th generation of IC engine advancement since the early 1900s?
Well, we've been through an amazing number of iterations of the earliest engines. And by the way, there were some excellent early engines.
Yep.
And by now we have added to that excellence the ability to mass produce. And the key to what's needed now is to use what is mass produced in better ways. But remarkably so, and importantly to our discussion, is the awareness that internal combustion engines can be much more efficient than they presently are and can use a much larger spectrum of fuel selections than they presently do.
And that they're going to have a very long life in the future, be used by us for many decades, and run at very high efficiencies and compete neck and neck with fuel cells.
Well, they can presently do better than fuel cells in many aspects.
Oh, wait. Let's back up for a minute.
Long-term endurance.
Some people are looking at the TV right now going, are you telling me an internal combustion engine can run more efficient than a fuel cell right now?
Well, I'm a fuel cell person. And what I know in this regard is that for full power production, endurance running, and net efficiency under those conditions, nothing beats the modern diesel engine, modern turbocharged or supercharged diesel engine.
For efficiency produced right now, year 2005, off the shelf, millions of engines, diesel holds the record in efficiency.
It does that.
Well, let's start talking about some internal combustion engine fundamentals so people can understand the wonderful stuff that we're talking about.
All right, well, it's a matter of heat management. And so one of the aspects of heat management that we really want to look into is the ultimate efficiency capability from any heat engine, any heat operation. And what is classic in this regard is the net efficiency of an engine, which is always limited to and never can exceed the highest temperature of the working fluid, and that would be the combustion byproducts or products of combustion, minus the lowest temperature that they achieve during expansion, divided by that highest temperature first achieved.
So what you're saying here with this formula is that if you have an internal combustion engine and you have a cylinder and you throw a bunch of fuel into it of any type and you ignite it, it's going to go bang. It's going to create a very high temperature of something, let's say 2,500 degrees Fahrenheit instantaneously before it exchanges to the cylinder walls. When the piston's all the way down, which we're about to show, and the gas is leaving the port and going to the exhaust and making its little bang, that temperature is TL, T low, and the cylinder gaseous temperature is TH, T high.
Well, the peak temperature reached is the T high. The point at which you exhaust or lose the motive power of that combination of air and byproducts of combustion, such as carbon dioxide if it's a hydrocarbon fuel, and water, and any other byproducts such as oxides of nitrogen
is TL. Okay, so the highest temperature reached, subtracting the lowest temperature, divided by the highest temperature, but it's not Fahrenheit.
Well, it can be, as it turns out, only true if you use absolute temperature. So this could be absolute temperature in Kelvin degrees or Rankine degrees, but it has to be consistently the absolute temperature.
So the Celsius scale is measured absolutely in Kelvin, and the Fahrenheit scale is measured absolutely in Rankine.
That's true. In the instance of using Celsius, well, you'd have the Celsius temperature that is commonly reported plus 273 to make the absolute temperature for this to be true as a limitation on ultimate efficiency.
But I guess the really important thing for the viewer to take away from this little lesson of this formula, whether you're ever going to use it or not, is to understand that the higher the temperature in the cylinder and the lower the temperature of the gas leaving the cylinder gives you the highest efficiency internal combustion engine.
That is true, and what it means by having a low temperature leaving the engine is that you've got work out of the gases. And what it means to have a high temperature is that you have a lot of potential energy from which you can extract motive power. Now, what's important in this regard is that this limitation for engines that are commonly on the street is seldom reached, because what we do instead is we lose a lot of the heat promptly on the surfaces of the combustion chamber.
The second that everything ignites, the heat wants to transfer to the cylinder walls, which is usually about the temperature of the engine coolant, so let's say about 200 degrees Fahrenheit to 230 degrees Fahrenheit, and it wants to go to the piston head as well.
It does that, but it also wants to vaporize or make an aerosol of any of the lubrication that happens to be in that upper cylinder.
Thus, the oil on the walls of the cylinder that keeps your engine from seizing, when the cylinder or the gas combusts, it vaporizes the oil and it's robbing some of our ultimate energy efficiency.
It robs energy and also gives unwanted hydrocarbons in the exhaust.
Because the oil doesn't break down as quickly or as easily as the gasoline or the natural gas or the hydrogen does that'd be thrown into the cylinder.
In fact, the oil is a very large molecule. What you get out of it are fractions of what it was as a large molecule.
Speaking of which, temperature high up here, you know, one of the things that's done in the automobile industry to reduce oxides and nitrogen production?
Sure.
They reduce their peak temperature in the cylinder.
Exhaust recirculation is often practiced. What we show is how to use more air, which is ultimately beneficial everywhere throughout the engine. And we'll get into the use of high boost fuels that enable a much larger air to fuel ratio
And we'll
to be commonly used.
And we'll talk about the current fuel to air ratio of gasoline to air and how that limits it. But let's look at what an internal combustion cylinder and piston looks like on the whiteboard.
All right. To just complete this, might say that if you look at hydrogen combustion, or if you look at gasoline combustion or any other hydrocarbon combustion, this upper temperature can be well over 5,000 degrees Fahrenheit.
5,000 degrees Fahrenheit.
Sure.
And it's not going to melt my cylinder?
Well, we'll try. And
We'll try.
Sure. And that's why we arrange for all the cooling virtually possible by spraying oil on your piston, by running coolant, either air or water or a solution of water and antifreeze, as close to the combustion chamber cylinder walls and through the head as possible.
Now, we are going to talk extensively about hydrogen all through these video series, but we are going to talk about gasoline and natural gas and other fuelings so people really understand. Really, the first thing to say is they really understand. And second is to say that they really understand the advantages of the hydrogen that we're going to be talking about.
Well, what's happening in the combustion chamber, if you look at the components of the engine, essential components being the piston, a way to express the thrust of the piston, typically through a crankshaft, and the cylinder arrangement with the head arrangement, and some form or another of spark ignition in the common engine, or timed fuel injection for compression ignition in the case of the diesel. But for the moment, take this as a spark ignited engine.
Like a regular gasoline engine.
Like a regular gasoline engine.
Because any gasoline engine can be a hydrogen engine.
That's true. Well, any diesel engine can be a hydrogen engine as well. Any Wankel engine can be a hydrogen engine as well.
So any internal combustion engine, which we refer to as heat engines generically, can be a hydrogen-fueled engine.
It's very true. What we're illustrating here is what you alluded to in terms of action within the combustion chamber. If you look within the combustion chamber and look at a section of what's typical in water-cooled types of engines, well, you find cooling passages arranged on the head, on the cylinder, and with oil cooling that carries away heat from the piston.
Now let's back up to your drawing of, and let's say this is a gasoline engine. Let's say its carburetor has a carburetor throttle body fueling system. Where's the air intake?
Well, if it's a carburetor throttle body system, well, you'll find a throttle that's restricting the airflow, and you'll find the fuel distributed in the vicinity of the throttle where the air is at a high velocity, so that the fuel becomes mixed with the air on the way into the combustion chamber at the time that the intake valve is open.
So on a throttle body or carbureted engine, the fuel and air is mixed before it goes down the passage,
That's right.
and then it goes to the valve.
That is right. The requirement of the homogeneous charge engine is always the same. It is to have a homogeneous mixture of air and fuel coming into the engine at any time that the intake valve is open and the piston is making a larger
And
volume.
homogeneous charge would refer to a proper ratio, nicely mixed up, completely mixed actually, of gasoline vapor and air.
It is. It's a same mixture then that's delivered to all portions of the combustion chamber. And then on ignition, first thing that happens on the beginning of combustion is that you get a rapid propagation of flame as it combines the fuel with the air that's there and releases quite a lot of the heat immediately on the head and the components of the head, such as the valves, on the piston surface and on the cylinder wall.
And thus that heat loss is going to lower our TH on the top and reduce our efficiency.
It does. It lowers the net amount of heat that's available for doing expansion and doing work then as you would wish it would have in the operation of the engine.
So in this example, the piston is pulling down and the air and the fuel is coming in.
Yes, this would be intake on a four-stroke engine, illustratively. And so what we're doing is we're, for the moment, prior to compressing, we're just making more volume, producing vacuum in the intake system. That vacuum helps vaporize and develop a homogeneous charge of fuel and air. Then this piston reverses as you go through bottom dead center, and we come up on compression. And that is, as we approach top dead center, the time that the ignition occurs and we start burning. And repeating myself, but that's when we have this heat loss, this immediate heat loss during the last stages of compression and during the cycle that follows, which is the power stroke of the engine.
Now this is an old engine. For the last 10 years, the automobile industry has been using what we call a multi-port fuel injection. Would you put in the illustration, where is the multi-port fuel injector on a standard automobile engine?
Well, on a
as of today, year
port,
2005.
Sure, on a port injection system, what we'd be doing is adding the fuel right at each cylinder's intake port. So what we'd be doing is bringing the fuel by an injector right at this location to spray fuel, hopefully, mostly at the location where the air is at the highest velocity, to again form a homogeneous charge.
So in this situation, the throttle body, the quote carburetor, which is no longer carburetor, it's called a throttle body, is just letting only air run down through here, and the fuel's injected at the last moment.
That's right. So you'd be bringing a supply of air into the vacuum that's formed by restricting air, and into that vacuum you'd be spraying fuel to form a homogeneous charge. At idle, this would be a high vacuum. At full power, it'd be much less. But it would still be the entire objective of this type of arrangement to produce a homogeneous charge. And again, to incur these losses of homogeneous charge fuel air near the surfaces that are cold, maintained cool for purposes of maintaining the integrity of the engine, of the components of the engine. So again, you'd incur a immediate heat loss, and this would account for a very large portion of what you buy at the pump.
Right.
And it, along with what is lost in the exhaust as much higher temperature heat as the exhaust valve opens, amounts to 2 units or 3 units of fuel potential energy and cost per unit that's delivered as power to the wheels.
A typical gasoline internal combustion engine in a car is about 17 to 23% efficient, depending upon the...
Yeah, you'd be throwing away, as it turns out, on the radiator and through the exhaust, 3 or 4 units of energy for each unit of energy that you were able to deliver as motive power. Now that motive power might be spent for other things than taking you down the road. That might be spent for air conditioning.
Right. And most people don't realize that the air conditioning can actually take up more horsepower than it takes to roll the vehicle down the road.
Yeah, in some portions of operation it probably is consuming quite a lot more.
The rule of thumb in internal combustion engines is that 1/3 of your energy goes to the crankshaft, 1/3 of your energy goes into the cooling system, your radiator, and 1/3 of your energy goes into the exhaust system. Really, that 1/3 that goes to the crankshaft is ate up by the parasitic loads of the AC, the fan, and everything else, losses to. But to give people listening or watching this an idea, that's the general rule of thumb, is that there's 2/3 of your energy, 1/3 going to the cooling system, 1/3 going into exhaust. And not to detract too much, but people wonder why diesels warm up so slowly, because they're not dumping that energy into the cooling system.
That's very true. Now the aspect that you brought up of diesels brings up then the charge distribution issue.
But we're going to go into diesels when we do when we start talking about diesels with propane fueling.
Sure.
People are going to see shortly in the video, they're going to show us that beautiful little 5 horsepower John Deere engine of yours.
Yeah.
Because everyone asks, how do I convert to hydrogen? How do I convert to natural gas? And they think it's a big hullabaloo and a bunch of complexity, and it's secret things and things aliens dropped in and magnets pointing in different directions. Will you show us how simple it is to make that little John Deere run on natural gas?
Well, on the
In this example up here with
Sure.
the, if we want to do a simple conversion, minding we'll get into some efficiency losses and power losses, how do we start adding natural gas to this system?
yeah, well, what we do in this regard for a ultimately simple conversion from petrol to an alternate fuel selection, such as you mentioned natural gas or hydrogen, is to bring the fuel into the air at a opportune place and time. The most opportune place and time would be to bring it without throttling, with no throttling of the air, and that would assume that you'd bring hydrogen and something with hydrogen in order to have an unthrottled engine, because we can support combustion of hydrogen almost in a full air-fuel ratio from 4 to 74%.
Now, if this was an off-the-shelf Ford vehicle that was natural gas powered with a throttle body, where would the natural gas injector be on the system?
Well, again, if that was a throttle body, it'd be up here at a throttle. But if it was a port injection, it would be here, aimed at the port of the intake valve.
So the smart place to inject natural gas, or anything, barring going directly into the cylinder, the smart place that everyone is using right now is right before the air intake.
Well, it is interesting in this regard that if you have a single cylinder, it makes not very much difference at all whether you're throttle body or port injection. But if you have multiple cylinders, you can use a single injector to feed 3 or 4 or however many cylinders you may have by distribution through an intake manifold.
Right.
So it's a cost reduction to have a single injector, a throttle body injector, compared to having a port injector per cylinder. And so you see both used, and what we've made note of is that gaseous fuels try to expand to fill all the space that's available. That's the nature of the gas. So if you're going to use a fuel such as natural gas or hydrogen or carbon monoxide or something other than petrol, as the engine may have been originally designed to use,
Pulverized cow manure.
pulverized cow manure, anything that would be combustible, what you're going to find is that those fuels try to fill the space available. So they take up air breathing capacity. And if you're using a fuel that is less dense in energy terms than what you've been using, then you need to arrange for making it dense or using a type of fluid dynamics that is ingestive of air as you bring the fuel in. One way to make more brake mean effective pressure or more net fuel and air available in the combustion chamber is to time the fuel delivery so that the momentum of the fuel ingests air or imparts momentum to air as it enters the combustion chamber.
At the same time. So when the piston is coming down and the intake valve opens and the air is rushing in, you want to time it to go at just that moment. Will you change this drawing to represent the 5 horsepower hydrogen John Deere?
Well, what we do in the 5 horsepower hydrogen John Deere,
Which could be any 5 horsepower or 1 horsepower or 10
Sure.
horsepower or 20 horsepower engine.
well, what we do in that regard is that we open the throttle.
Okay, now by opening the throttle, you mean the carburetor is gone.
It's gone. You either dispose of all the apparatus entirely and put an air filter, and we'll show both ways, or you can just make the throttle wide open like you're going to run full power all the time, but instead you attenuate the flow of fuel by a valve and deliver to a point where it's aimed to go into the combustion chamber at the time the intake valve opens.
So hold it, you're not mixing it at the opening, you're putting the little tube with the hydrogen coming out of it all the way right there at the valve.
That's right. Now, we're taking it all the way to the point that extends from the valve to the intake valve, so that the momentum of the fuel entering pushes more air on its entry to the combustion chamber.
But in this case, there's no timed injector. It's not going psst, 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 psst with each cylinder. It's just continually flowing the hydrogen in at a steady state.
We show both ways, but in this instance we're showing the probable use of a needle valve that's in a slow adjustment from idle to full speed, so you wouldn't be turning it off and on each time that the piston was going through
So
an
this
intake.
is as simple as it gets.
This is as simple as you might wish that it could be. Now, the other thing that you may wish to do is to experimentally find the optimum timing for the fuel combustion rate that's established by your fuel choice. And the way to do that in most small engines is to develop a set of marks on the flywheel so that you can adjust the magneto to fire the plug to make a spark for firing the cylinder at a time that is commensurate with the fuel combustion rate that's been selected.
See, that's a whole different thing. People don't realize that basically the only thing you have to do to convert to a hydrogen engine is what we just showed, but it's going to be more advantageous if you change the timing of the engine.
One way to change the timing of the engine is to remove the key that times the flywheel for operation on gasoline, so you can rotate the flywheel with respect to the crankshaft and develop a different timing, usually a much later ignition timing, which is highly advantageous to the combustion chamber retention of heat.
I think we're going to have to draw another drawing over here and show what timing really is on a gas engine versus a hydrogen engine and why it's detonated pre-top dead center on the gas.
Well, you might even think of it right here. What happens in sequence is that this piston comes to a higher and higher location, ultimately reaching top dead center.
Which is as high as it will possibly go.
High as it can get before the crank rotates over the top dead center position and starts going through a power stroke.
So if someone says TDC or top dead center, that's what they're talking about. It's at the top and ready to go down.
That's right. So in the case of hydrogen or hydrogen boosted, which we call high boost fuels, which can be an addition of hydrogen to gasoline or propane or natural gas or landfill gas or producer gas or whatever you may be using, if you're using some hydrogen, it'll burn faster than if you were using a hydrocarbon, maybe 9 times faster. So you'll have a much better net efficiency in the engine by making the timing later.
So what's the flame speed of gasoline?
Oh, well, it says 4,000.
And the flame speed of hydrogen?
Oh, nearly 10 times as much.
40,000.
That's right.
And that's measured
Approaching.
in feet per second.
It is.
So if you had 40,000 feet of hydrogen in an ideal perfect tube with the right air mixture and you lit it at one end, 40,000 feet, that'd be 8 miles, it'd go all the way down in 1 second.
Yeah, it would make a, depends on, incidentally, the
Ideal
walls.
theoretical tube for purposes, for the listener, 40,000 feet in 1 second.
Depends. Well, how it really works, in fact, in combustion events is that hydrogen comes already subdivided as a very small molecule.
Right.
And so you don't have to evaporate it, you don't have to crack it to get it to burn as you do large molecules such as gasoline or diesel fuel, or
Which slows the propagation down.
which slows the propagation down. But it's also very true that hydrogen can find oxygen much more rapidly than these other fuels because it's moving independently as a small molecule much, much faster than large molecules will.
So we're talking about advancing the timing, though. Where is the gasoline engine detonated?
Well, if the gasoline engine is ignited according to its best operation, it'll be considerably before top dead center.
And so
maybe in crank rotation.
basically before the crank down here is getting ready to turn over, and we're actually detonating the gasoline and putting back work on the crank.
That's right. What we're doing is developing pressure during compression from the combustion event.
So it's ignited before it's at top dead center.
That's right. So it gives a requirement to have a flywheel, a considerably massive, high rotational inertia flywheel, to carry the piston even through this back pressure that's being developed during combustion and being developed just by compression.
And so some of this back pressure is also a loss of efficiency.
Well, it is. It's a very large loss of efficiency along with a vacuum that's produced typically for vaporizing petrol. And it's a further loss of efficiency by all the heat transfer that goes out to the combustion chamber walls, to the piston, to the head components.
One of the reasons we have to do that is because of the slower flame propagation of gasoline and air.
That's right. Otherwise, you'd be losing the gasoline through the exhaust system, because it wouldn't complete combustion at the speeds that we want to run engines.
So hydrogen, this is going to be down here at top dead center.
Yeah, virtually at top dead center, you burn the hydrogen, and then the expansive energy is almost entirely delivered
the downstroke, on the
power
rotation
stroke
of the piston.
That's right, during making what you need for torque.
Yeah, sorry, during the rotation of the crankshaft. So the lesson for the viewer to take away is that the closer you detonate to top dead center or at top dead center, the less back work you have on the engine, the higher efficiency, and the more miles you get for a dollar of your fuel being used.
Indeed, and you make the engine last much longer.
Oh, really?
By not having this work being done during compression, you save the load on the bearings, you save the friction that's produced on the wall of the piston as it's being thrust against the wall.
So we're pushing against, it's like pushing and pulling, saying, oh yeah, that would wear down the bearings a bit, wouldn't it?
Well, and the cylinder, and it also burns off the lubrication, and it also mingles the fuel with the lubricant by having it thrust during these partial combustion and quench events that occurs into that film that you wished would have maintained itself as a non-cut or non-diluted film.
No, well, everyone's screaming right now, let's see some engines, so let's stop the classroom for now, and we're going to go show some people some hydrogen internal combustion engines.
All right, I may just close, however, in making note that the other major equation that we want to keep track of in that regard, and we'll be making reference to, is that the power that we can develop, and horsepower being the typical measure of power, the power that we can develop will be equal to the pressure that we develop as a sum of all the pressures, the sum of the intake, some of the compression, some of the power, and some of the exhaust stroke events, times the length through which we do expansion. This would be the travel of the piston, times the area of the piston, or the area of the rotor in a Wankel engine that's expressed across the pressure difference, times the number of cycles that we can make per unit time.
Okay, you have just some of the people are going, oh no.
Well,
what you're saying is that basically the higher the pressure, the longer the length of the stroke of the piston, so the longer this is, times the bigger area of the piston, the larger diameter of the piston.
That's right.
Multiplied by how fast we can run that thing in RPMs per minute.
That's right.
Is going to, all four of those things contribute to having the best horsepower, the best efficiency.
That's right. By making the timing, as we just mentioned, to tie this together, a much later ignition timing, as we are able to do by hydrogen facilitated burning,
that gets us more power.
Gets us more power.
Because we're not pushing back against the cylinder when we're not supposed to.
That's right. It gets us much, much more useful power.
The L, the length.
The L and the A are fixed by how you design and select your engine.
They're kind of stuck with that because they got their car.
That's the displacement. The N, however, is very much a subject of the number of degrees of rotation to complete combustion. Hydrogen holds the world's record for being the fastest burning, so you can greatly increase the complete cycles per unit time of operation and increase the N along with the P in the PLAN formula.
So we can have a higher pressure and we can run at a higher RPM, which is the N.
That's right.
The L is the length of the piston, the A is the area. The thing that determines N in a modern internal combustion engine is the metallurgy, the strength, and the size and mass of that L and A, the piston and the area, because a smaller piston will run up and down faster without throwing itself apart than a larger one will.
Well, it depends a lot on the integrity of the lubricant, the upper cylinder lubricant, and it depends on, as you mentioned, the integrity of the material selected.
Right.
But you can greatly improve their operation as they exist, whatever engine you may have started with, by reducing the heat transfer to the piston, reducing the heat transfer to the cylinder, not compromising the lubricant that you depend upon in that reciprocating motion, and by not heating the valve or the components of the head by, as it turns out, this inadvertent transfer of heat on these homogeneous charge operations, particularly during compression as necessitated by the slow-burning hydrocarbon fuels.
And people are going to ask, where do you get an engine that has an optimal P, an optimal A, an optimal L, and optimal N? And the answer to that is the X engine, which you will be seeing on this video.
That's very true.